Hello viewers, last time we stated the important theorem of complex analysis, almost the theorem in complex analysis, namely the Cauchys theorem, and in this session we are going to prove the Cauchys theorem. So, let me give the statement of the theorem once again, Cauchys theorem. Okay. So, the Cauchys theorem says that for a rectangle, okay, so this is one version of Cauchys theorem. It says that let R be a rectangle or rectangular region R equals set of all x plus I y such that x is in between a and b and y is in between c and d. Okay. And we will assume that a is not equal to b and c is not equal to d for non-triviality. Okay. So, it is really a rectangular region with some area, okay. And let f be analytic on an open set containing this rectangular region R, okay. Then the conclusion is that then the contour integration of f of z dz on the boundary of the rectangle R, okay, oriented in the positive sense is equal to 0. Okay. And once we prove this theorem, it does not matter how you orient the boundary of the rectangle, because once it is 0, then the rectangle boundary oriented in the opposite direction will also give you a contour integral equal to 0. Okay. So the orientation really does not matter after we prove the theorem. Okay. So, and hence this notation is being casual about the orientation. Okay. So, here is the proof of the theorem. Okay. So, let us start with a notation. Okay. So, here is a notation just to avoid writing too much. Let me give you a notation. Eta of some t is a rectangle, let us say, okay, is essentially the contour integral along the boundary of t f of z dz for any rectangular region T. Okay, so, that is the notation I will use. Okay. So, let us start with a picture. So, here is the rectangular region R. Oops. Okay. And let us subdivide this rectangle into 4 equal pieces. Okay. So, in terms of area, let us say. Okay. So, here is the contour del r, okay, which appears here in the contour integral, the statement of the theorem. Okay. So, like I mentioned last time, what we do is we take these contours, okay, the rectangle R, the rectangular region R is divided into 4 rectangular regions, okay, and then we take these contours okay. So, this is just a picture. What these 4 contours actually are they traverse the sides of the rectangle, okay, and those inside lines. Okay. So, just for lack of space, I am drawing a slightly smaller rectangle inside to indicate that the contour is going on the rectangle and on the subdivisions, the lines which are a part of the subdivision. Okay. So, for example, here is a contour like this, okay, which actually should have been this contour, which is wiggly right now. Okay. So, instead of drawing such wiggly things, I just drew them inside. Okay. So, R is now union of 4 rectangular regions, R 1, okay, union R 2, union R 3, union R 4. Okay. So, I am naming them R superscript parentheses 1, 2, 3, 4, etc. Okay. And so, okay. And since the inside lines, you can see that when you consider the boundary of these R 1, R 2, R 3, R 4, you see that the inside lines have contour integration of f in one direction and then in the opposite direction. Okay. So, for example, this line right here, okay, has a contour integration along this and along this. Okay. So, they cancel each other. Okay. So, what I mean is that when you consider the contour integral of f of z dz on dou r, okay, then on del r, this is equal to the contour integral on del r 1 of f of z dz plus the contour integral on del r 2 f of z dz. I apologize, I am taking R 1 on top, R 2 like that, okay, del R 3 like that, f of z dz plus integral dou R 4 f of z dz. Okay. And since like I mentioned, the contour integral on the insides cancel due to opposite directions, all we are left with is contour integral along the boundary of R. Okay. So, it is easy to see why this equality is true from the above picture. Okay. And from our notation we had up there, eta of R is eta of R 1 like that plus eta of R 2 plus eta of R 3 plus eta of R 4. Okay. So, we can conclude that there is some I, okay, 1 less than or equal to I less than or equal to 4. Okay. So, essentially one of these is at least 1/4 of eta of r in terms of absolute value. Okay. So, there is some I such that the modulus of eta of r I, okay, is greater than or equal to 1/4 of modulus of eta of r. Okay. That is clear, because if the moduli of any one of these is strictly less than 1/4 of the modulus of eta of r, then you get a contradiction from a triangle inequality, let us say. Okay. So, so there should be one I such that this should hold. Okay. So, that we will preserve. Okay. So, we will preserve this inequality. Okay. So, call, or let us call this R I as R 1. Okay. So, now I am saying that that particular R I for which the above holds, we will call that rectangle R 1. Now, there could be more than one rectangle for which this holds. Among R 1, R 2, R 3, R 4, there could be more than one for which this holds. Then in that case, you just choose one of them, you can randomly pick one of them, okay, and call that as R 1. Okay. So, in case there is more than one I with, okay, so let me call this inequality 1, okay, with okay, for which 1 holds, then choose one of them arbitrarily, it does not matter, as R 1. Okay. So, we will call that R 1, and then let us pretend that the top left rectangle was R 1. Okay. So, let me go back to this picture. Let us pretend that there is R 1. Okay. So, in that event, you take R 1 and do the same, divide it into 4 equal pieces, okay, and continue the process. Okay. So, divide R 1, okay, into 4 equal rectangles. By equal, I mean equal in terms of area, let us say. Okay. So, okay, and call these R 1 1, R 1 2, R 1 3 and R 1 4. Okay. And once again there exists, for the same triangle inequality reasons, okay, there exists an I 1 less than or equal to I less than or equal to 4, such that the modulus of eta of R 1 I, okay, is at least 1/4 of the modulus of eta of R 1 this time. Okay. And R 1 was chosen so that its modulus was greater than or equal to 1/4 of the modulus of R, modulus of eta of R rather. So, this is greater than or equal to 1/4 times 1/4 of modulus of eta of R. Okay. So, call this R 1 I as R 2. Okay. So, once again, in case there is in case of more than one such I, okay, etcetera, etcetera, do the same, you just pick one arbitrarily. Okay. And then you have R 1 R 2, okay, which is produced like that. Okay, and continue this process. Okay. So, continue this process to obtain a sequence of rectangles R 1, R 2, etcetera. Okay. So, R 1 of course, it contains R 2 and initially R 1 was contained in R, okay, and then R 2 contains R 3, etcetera. Okay. So, continue this process. Now, so we get this nested sequence of rectangles and rectangular regions rather, okay, and what's nice about these is that we have an estimate that eta of R n of the next rectangle, okay, is at least 4 power minus n times the modulus of eta of R, right. So, for example, here you observe that eta of R 2, we are going to call this R 2. So, eta of R 2 in modulus is greater than or equal to 4 power minus 2 modulus of eta of R. Okay. So, continuing this you get eta of R n is at least 4 power minus n in modulus of eta of R. Okay. And then so, we will preserve this inequality, okay, we will call this, let us say 2. Okay. Now, then these are nested sequence of rectangular regions, okay, R 1, R 2, etcetera. So, from a theorem in topology, we know that the intersection of these is non-empty, okay, and these rectangles are shrinking in area, each one is 1/4 of the previous one, Okay. So, they converge to a certain point because the intersection, their intersection is non-empty. Okay. So, we will say that, okay, so these rectangles converge to a point z star. Okay. Same z star, of course, that is inside the rectangular region R. Okay. And then it is in the following sense. Okay. So, given a delta positive, okay, there is a natural number capital N such that R capital N is contained in set of all z such that the modulus of z minus z star is strictly less than delta. Okay. So, if you consider z star, which is the point of convergence of these rectangles, and you consider a delta ball around it. Okay. So, this is a ball of radius delta. Okay. Then there is a natural number n such that the nth rectangle is contained in this ball. Okay. This R capital N. Okay. And once R n is contained in there, you know that R n plus 1 is which is contained in R n is also contained in there. Okay. So, I e, so notice R n is contained in z such that mod z minus z star is strictly less than delta for all n greater than or equal to capital N, right, because these are nested sequence of rectangles. Okay. So, if R capital N is in there, all further rectangles are in there. So, so now in the convergence of these rectangles to the point z star is in this sense, is in this particular sense. Okay. So, now we are free to choose a delta, and given any delta positive, we know that there is going to be some rectangle, and such that all the rectangles from there on will be in the above sequence will be in this delta ball. Okay. So, now we are going to choose this delta in a certain way. Okay. So, here is the way we choose delta. So, we know that given we know that f is analytic in an open set containing the rectangle capital R. Okay. So, given epsilon greater than 0, there is a delta positive such that okay, whenever okay, the modulus of z minus z star is strictly less than delta, the modulus of f of z minus f of z star okay, minus f prime of z star times z minus z star okay, is strictly less than epsilon times modulus of z minus z star. Okay, that is because this function f is analytic at z star. Okay, we use the definition of analyticity or differentiability at z star. So, whenever so given epsilon greater than 0, there is a delta greater than 0 such that whenever these z's are in a delta neighborhood of z star, this inequality holds. Okay. So, this we will call this as inequality 3, right. This is I mean 3 is clear from definition of differentiability f of z minus f of z star okay, okay, divided by z minus z star. The limit of this as z approaches z star okay, is equal to f prime of z, z star rather. Okay. So, from this we get this inequality. Okay. So, or this limit means the above inequality. Okay. So, now let epsilon greater than 0 be given, okay. Then choose. So, now this is a fresh epsilon we start with, let epsilon greater than 0 be given, okay. Choose delta positive such that 3 holds, okay. And given, okay, and after choosing this delta, okay, obtain an n, okay, a natural number n such that this here holds, such that R n is contained in set of all z such that mod z minus z star is strictly less than delta. Okay. We saw that given any positive delta, this can be done. So, so now after choosing this delta, we can get such a containment. Okay. We can get such a natural number. We will make some observation by the fundamental theorem of calculus. Okay, the complex version. Okay. So, by the fundamental theorem of calculus, we know that the integration, okay, the contour integration of 1, the complex function 1 dz on the boundary of R n, okay, is 0, because 1 is the derivative of z on all of the complex plane. So, in particular on an open set containing this rectangle R n. Okay. And likewise, the contour integration of the function z dz, okay, on the boundary of R n, okay, is also 0. Okay. So, we will need these two pieces from which are conclusions from the fundamental theorem of calculus. Okay. Of course, the second equality here, or the second value of the integral, follows from the fact that z is the derivative of the function z squared by 2 on all of the complex plane. Okay. So, so we will use these two, okay. And notice that the modulus of the contour integral on the boundary of R n, okay. I have not chosen what n is here, but let us say boundary of R n of f of z minus f of z star minus f prime of z star times z minus z star dz. Okay. So, all this dz, okay, is less than or equal to the modulus of the integration, the contour integration on the boundary of R n of epsilon times z minus z star dz. Okay. And this inequality is right from here 3. Okay, I am using 3 and then I can conclude this thing here. Okay. So, what I get is, this is the integration, the contour integration of f of z dz minus the contour integration on the boundary of R n, okay, f of z star dz minus the contour integration of f prime of z star times z dz, okay, plus the contour integration of f prime of z star times z star times the contour integration of 1 dz. So, that is in the left hand side of this inequality, okay. And Yeah. So, you notice that f prime, I mean I am writing this way because f prime of z star is a constant and z star is a constant. Okay. So, you notice that let me pick a different color, maybe this one. Okay. So, this one and this one and this one, all these three are 0 because the contour integration of 1 or z, okay, on the contour boundary of R n are 0. Okay. So, this is less than or equal to epsilon times the contour integration on R n, okay, of the absolute or modulus of z minus z star times mod d z. Okay. So, these are zeros, these yellow things are zeros. So, what I get is that the modulus of the contour integration of f of z dz on R n, okay, is less than or equal to epsilon times. Now, I am going to use the estimation theorem we saw in the last session, okay, and say that the modulus of z minus z star, okay, in R n, okay, is at most the length of the diagonal, right. So, here is the picture. So, if you look at z star, okay, and here is R n containing z star could be anywhere in R n. Okay. So, the maximum value of the modulus of z minus z star as z varies on the boundary of this R n is essentially the length of the diagonal, because z star, for example, could be a point on this diagonal itself, one of the corners. Okay, then this is the, if this is the point z, then z is the diagonal length away from z star. Okay. So, that is the maximum distance. So, this is less than or equal to z minus z star is at most d n, where d n equals the length of diagonal of R n. Okay. So, this is d n, okay, and then I am left with the integration of mod d z on boundary of R n, and we know that that is the length of the boundary of R n, okay, which is essentially the perimeter. Okay. So, let me write that as L n. Okay. So, L n equals the perimeter of the rectangular region R n. Okay. And the way we have chosen these rectangles by subdividing them into 4 pieces of equal area, we have the following: this d n, okay, will be 2 power minus n times d, where d equals length of the diagonal of R. Okay. And L n, which is the perimeter of the nth rectangle, okay, is going to be 2 power minus n times L, okay, where L equals perimeter of R. Perimeter of R. Okay. So, what we get is the modulus of eta of R n is less than or equal to epsilon times d n times epsilon times d n times L n, which is 2 power minus n times d times 2 power minus n times L, which is 4 power minus n times d times L. Okay. So, this we will call as inequality 4. Okay, maybe I use 3. So, I am going to call this 4. Yeah, okay, 4. Okay. So, from 1 and 4 I will allow me to go back to 1, remind you what 1 is, or maybe 2 actually. Okay. So, 2 tells us that the modulus of eta of R n is at least so much, okay, and 4 tells us that the modulus of eta of R n is at most so much. Okay. So, we can compare these two quantities. Okay. From 2 and 4, we conclude that the modulus of eta of R n. Okay. So, 4 power minus n modulus of eta of R is less than or equal to modulus of eta of R n, okay. And then from 4 this is epsilon times 4 power minus n times d L. Okay. So, we will ignore the middle part, namely the modulus of eta of R n, and conclude that the modulus of eta of R which we are interested in is less than or equal to epsilon times d L. Okay. So, this tells us that well, okay. So, this tells us that since epsilon is arbitrary, okay, that eta modulus of eta of R is actually equal to 0. D and L are fixed constants. We have started with a rectangular region. Okay. So, the modulus of eta of R has to be 0, okay, which implies eta of R itself. So, this proves the Cauchy's theorem. Okay. And so, let us before proceeding further, let us see the interpretation or one physical interpretation of Cauchy's theorem. So, there is a I am going to give the fluid mechanics interpretation of what Cauchy's theorem is telling us. There is an equivalent version for electricity one can or for electric fields that one can construct, but nevertheless here is a physical, okay, a physical interpretation. Okay, of Cauchy's theorem. So, few sessions earlier we saw that when one considers a two-dimensional fluid flows, then one can model it using complex analysis, okay, and then the velocity function at each point is the conjugate of an analytic function if we assume that the fluid flow is irrotational and does not have sources or sinks. Okay. So, irrotational just means that the fluid is not just rotating around a point, roughly speaking, okay, and then it is not stagnant anywhere. Okay. And likewise, source or a sink tells us that there is no fluid produced anywhere during the flow, okay, or there is no fluid which is which disappears, no volume of fluid which disappears during the flow. Okay. So, if we make these assumptions, then we get that the velocity field, okay, of a fluid flow is the conjugate of an analytic function. Okay. So, let us first start by interpreting what the line integral means in this context. Okay. So, let me draw a picture first. So, here is a certain conduit, okay, a deep channel perhaps, okay, and then we can assume that if we consider parallel strips along this conduit anywhere, then the flow is two dimensional. Okay. So, here is a point x y, let us say, let us model it as x y, then there is a certain velocity vector based at that point, okay, and then there are points everywhere, and at each point there is a certain velocity to the fluid, okay, and v of x y, okay, denote the velocity of the fluid at a point x comma y, okay, and we write v of x y is p of x y plus I times q of x y, okay, where p indicates the fluid velocity parallel to the x axis. Okay, so, we will have some imaginary, or we will imagine some axis here, okay, this is an x axis, this is a y axis, etc., okay, in that conduit, and then we have p is the velocity along x axis and q is the velocity along y axis. Okay. Then v of x y is a conjugate of, well, let me write that as z, okay, where f is analytic, okay, provided that the fluid flow is irrotational, okay, that is to say that the curl of the velocity field is 0, okay, and does not have sources or sinks. The fluid flow does not have sources or sinks, says that the divergence of this field is 0, of v is 0. Okay. And these two, we saw these two conditions actually allow us to form the Cauchy-Riemann equations. Okay. They allow us to conclude that the Cauchy-Riemann equations hold, okay, for the function v bar, okay, which is f. So, with these conditions, we have v is the conjugate of an analytic function. Okay. Now, we will first start by interpreting a line integral. So, let us for simplicity assume that gamma is a certain arc like that. Okay, it is a curve. So, in terms of what we have been describing, gamma is what I have drawn here is the trace of a gamma, of a certain gamma, which is a parameterized curve. And so, and remember that the interpretation of line integral is independent of how we actually parameterize the curve itself. Okay. So, I will just call this piece of string, okay, this piece of curve here as a contour gamma, okay, and I am keeping it simple, I am not allowing it to self intersect or anything. Okay. So, here is a simple piece, and let us now assume f of z is, well, f of z is p of x y minus I times q of x y from above, because v is p plus I q. Okay. And so, the contour integral of f of z dz along this kind of smooth curve, okay, is the integration from a to b, where gamma is parameterized from a to b, okay, to c, of f of gamma of t, gamma prime of t dt. Okay. So, if I call gamma of t as x of t plus I times y of t, okay. So, gamma after all has its image in C, okay, then I can write this line integral as a to b, f is p of, okay, gamma of t. Gamma of t is a point in the complex plane. Okay. So, strictly I should be writing x of t comma y of t. So, p p of x of t comma y of t, okay, plus or rather minus I times q of x of t comma y of t, okay, and then gamma prime. So, times gamma prime is x prime of t plus I times y prime of t dt. Okay. So, I will write this as, for simplicity I will ignore, I will drop writing x of t, y of t, etcetera. I will simply write this as p minus I q times x prime plus I y prime. Okay. Since what each one is a function of is clear from the context. Okay. So, this is that. So, now let me multiply these two. So, a to b p x prime plus q y prime plus I times p y prime minus q x prime and then dt, all this dt. Okay. So, we can write this as, or split this into integration from a to b p x prime plus q y prime plus I times integration from a to b of p y prime minus q x prime dt. Okay. So, now we will interpret each of these integrals to understand what this line integral is doing. Okay. So, here is the curve gamma, okay, and at a point t in time, okay, here is the point gamma of t, let us say. Okay. Gamma prime of t gives you the tangent vector to this curve at a point gamma of t. Okay. So, here is gamma prime of t, which is the tangent vector to this curve, okay, and v, which is let us say the velocity vector based at this point gamma of t, is somewhat like that, let us assume. Okay. Then you notice that the integrand here, I am sorry, this is dt here. Okay. The integrand here in the first integral p x prime plus q y prime, okay, can be interpreted as the dot product of v with the tangent vector gamma prime of t. Okay. So, here is the velocity vector v. Okay. So, so gamma prime of t, I mean v times gamma v dot gamma prime of t is the first integrand. Okay. So, the real part, what it does is okay, it takes the dot product of the tangent vector with the velocity vector, okay, and plus I times, what about the imaginary part? The imaginary part is the dot product of, or can be interpreted as the dot product of the vector p q, let us say, okay, with the vector y prime minus x prime. Okay. Now, y prime minus x prime is a vector which is perpendicular to x prime comma y prime. So, it is a vector perpendicular to the tangent to the curve, which means it is a normal to the curve, okay, and from the direction y prime minus x prime we can make out that it is pointing inwards, whatever inwards means. So, which means it is pointing from the left of the curve to the right of the curve. Okay. So, okay, from the region left of the curve to the region right of the curve, okay, starting from the point gamma prime of t. Okay. So, this integrand in the imaginary part can be interpreted as the dot product of v with the normal in that particular direction, okay, dt. Okay. So, what is the physical interpretation of these two? Velocity when integrated along a direction, if we assume is the displacement of the fluid or the amount of fluid. Okay. So, then this integrand, in this integration actually gives you the displacement of fluid along the curve gamma Okay, and this imaginary part is this stands for the displacement of fluid okay, into okay. This does not, I mean, this into does not make sense for a non closed curve, but let me just write it, it is into the inside of gamma. Okay. So, after writing it, let me explain that it is called the flux of this velocity vector okay, with respect to this curve at the point gamma of t. Okay. So, it is the component of the velocity which is perpendicular to this particular arc. Okay. So, then when we have a closed curve, okay, so for a simple closed curve contour, okay, or from what we have proved, okay, so this is more general, but for a rectangular region at least we proved the Cauchys theorem. Okay. So, for a rectangular region Cauchys theorem says that the integration of f of z dz, where f is analytic, okay, is equal to 0, okay, where f is analytic on and inside the contour R. Okay. So, from the fluid flow interpretation, okay, so what we have is, if the fluid flow if the velocity field V is f of z bar for an analytic function f on and inside this rectangular region R, what we can say is that there is no amount of fluid. Okay. This is telling you that the integration of f of z dz on dou R is equal to real part of the integration of f of z dz on the boundary of R plus I times the imaginary part of this, which is 0, okay, which is given to be 0 by this okay, by Cauchy's theorem. So, since the real part and the imaginary part are both 0, okay, what this part is telling you is that the fluid displacement, okay, or fluid displaced, okay, along the curve, along the closed curve, that is important, okay, along the closed curve is 0. Okay. So, there is no fluid which actually keeps flowing around a contour. Okay. So, there is no stagnation in that sense. Okay. And the imaginary part being 0 tells us that okay, once again averts that there are no okay, there is no fluid trapped inside the rectangular region. Okay. So, whatever fluid crosses the rectangular the boundary of the rectangular region or into the rectangular region has to come out. Okay. So, so there is no fluid which remains trapped, that is what this says. Okay. Because when you add up the normal components of this velocity, they give you the total fluid, okay, which remains inside. So, that is 0, tells you that there is no fluid which is trapped. Okay. So, this is an interpretation, physical interpretation of Cauchy's theorem. Next, let us consider the following extension of Cauchy's theorem, a mild extension of Cauchy's theorem. Okay. So, let f of z be analytic on and inside, okay, on an open set containing a rectangle R, okay, a rectangular region. Okay, by rectangle R I mean the rectangular region R, okay, except at a point zeta inside, okay, which is in the interior of this region. Okay. So, if it is true that if the limit as z goes to this point, the special point zeta, z minus zeta times f of z, if this limit is equal to 0, okay, then the integration, okay, on the boundary of this rectangular region R of f of z dz is still going to be 0. Okay. So, this is modified Cauchy's theorem. So, we have the similar setting or almost the same setting, except that there is a special point zeta where f is not exactly analytic, f is not analytic, perhaps it is not even defined there, but what is important is it satisfies this mysterious condition. Okay. Then it is still true that the integration on the boundary of R of f of z dz is going to give us 0. Okay. So, we will decode this later, but this mysterious condition later, but for now this can be considered as a slight extension of Cauchy's theorem. Okay. So, let us see how or why this is true. Okay. So, what we do is, here is the schematic. Okay. So, here is the rectangular region R, okay, and then there is this special point zeta which is in the interior of R. Okay. So, what we do is we divide this rectangle, okay, subdivide this rectangle into further rectangles and consider a small enough rectangle around the special point zeta. Okay. So, we will use contour integration on the boundary of R in the counterclockwise direction. Okay. So, this is dou R is the boundary of R in the positive direction. Okay. And then using the Cauchy's theorem, okay, so we will use contour integration like that, and using the Cauchy's theorem that we just proved, we will say that the integration, okay, on any of these R1, R2, etc., okay, any of these rectangles, I will be a little informal about this. I will just say the on boundary of any of R i's, okay, the integration of f of z dz is equal to 0. Okay, that we know because f is analytic on an open set containing this whole rectangular region, for example. Okay. Now, perhaps except on this little rectangle which surrounds the special point zeta. Okay. So, for that special point zeta, I am going to make a special adjustment. Okay. So, firstly notice that the integration on the boundary of R in the counterclockwise direction, okay, is now equal to of f of z dz is equal to the integration on this smaller rectangular region. Okay. I can assume that to be a square. I can adjust these sides so that that small rectangle is actually a square. Okay. So, that I will say that is R zeta, which stands for the rectangle containing zeta. Okay. So, the integration is equal to the integration on boundary of the rectangle R zeta of f of z. Okay. So, we will save this equation 1, okay, and with the given condition. Okay. So, given epsilon greater than 0, since limit as z goes to zeta of z minus zeta times f of z is equal to 0, given epsilon 0 greater than 0, there is a delta positive, okay, such that whenever modulus of z minus zeta is strictly less than delta, okay, the modulus of z minus zeta times the modulus of f of z, okay, is strictly less than epsilon, because the limit as z goes to zeta of this quantity is 0. Okay. The modulus of this is arbitrarily less as z goes to zeta. Okay. So, I can do this, and what this is telling me is that the modulus of f of z by or is strictly less than epsilon divided by modulus of z minus zeta whenever this occurs. Okay. So, I can choose this delta. Okay. Well, given epsilon, I can choose this delta so that 2 occurs. Okay. And by this, what we have is, by the estimation theorem we had in the last session, okay, the modulus of the integration over dou r zeta of f of z dz, okay, is less than or equal to the integration over dou r zeta of the modulus of f of z modulus dz, okay, which is now by 2. This is strictly less than epsilon, okay, or I can say this is less than or equal to epsilon times integration over dou r zeta of modulus of dz by modulus of z minus zeta. Okay. So, by choosing r zeta to be small enough, okay, I can notice I can always adjust these vertical lines to make this r zeta, okay, as small as possible. That is here r zeta, okay, that is the rectangle r zeta. I can make it a square centered at zeta, and I can make it as small as I like. Okay. So, so then I have this estimate. Okay. So, when r zeta is a square centered at zeta, and your z varies on the boundary of r zeta. Okay. What we have is the modulus of z minus zeta for z belonging to dou r zeta, okay, is such that the modulus of z minus zeta, okay, is less than or is greater than or equal to, okay, is greater than or equal to s by 2, okay, where s is the side of r zeta, side length of r zeta of the rectangular region r zeta. Okay. So, when this occurs, 1 by modulus of z minus zeta, okay, is less than or equal to 2 by s. Okay. So, the modulus of d zeta dz, okay, on the boundary of r zeta divided by modulus of z minus zeta, okay, is less than or equal to 2 by s times the integration over dou r zeta of modulus of dz, okay, and that is nothing but the length of this curve of this curve dou r zeta, okay, which is 2 by s times 4 s. Okay. So, this is 8 s, sorry 8 rather. Okay. So, this quantity is less than or equal to 8. Okay. So, this is less than or equal to 8 epsilon. Okay. Since epsilon is arbitrary, okay, so since epsilon greater than 0 is arbitrary, so given any epsilon I can do this. Okay. What I conclude is that the integration, the modulus of this integration is 0. Okay. So, the only complex number with 0 modulus is 0. So, the integration over dou r of f of z dz is actually this is zeta, actually r zeta, but this is equal to integration over dou r of f of z dz by 1, okay, by the equation 1 here. Okay. So, this is equal to 0. Okay. So, that proves the contention. Okay. So, with this I will stop this lecture here.